in my infinite cheapness, I'm going to use this same background because we are still talking about chemical compound structures. We're still talking about electron dot and Lewis structures, but I want to look at some different examples. So it's the same setup. Write the electron dot structure and the Lewis structure for each of the following compounds. And electron dot structures, we got pairs of dots, whether they're for bonding or non-bonding purposes. Lewis structures, you got lines and dots. That's it. Do not outsmart yourselves. All right, so the first one we're going to look at here, we'll say something like diatomic hydrogen, H2. So when hydrogen occurs in nature, it occurs as H2. It's not just an H by itself. And there's a good reason why. All right, hydrogen, group 1 of the periodic table, 1 dot, 1 valence electron, 2 would be ideal. As you look at this, hopefully based on the last video, you're saying to yourselves, hey, 1 dot, 1 potential bonding location. And that pause was there for you to think, shouldn't it be bonding to something? And the answer is yes. This is a fairly high energy species because it's going to bond to something, right? Why do bonds form to reach a lower energy state? Well, 1 single dot, a potential bonding location, is a high energy state. It's going to bond to something. So pure hydrogen, it turns out, is when we have another hydrogen with its 1 dot, and then they form a bond, right? So if I'm going to set this up like we had last time, I have to show like, oh, hydrogen, dot, dot, hydrogen, right? And hydrogen, line, hydrogen. So this would be our electron dot and our Lewis structure. And I don't have any external dots on these because hydrogen, full of valence orbitals, is just the S. It doesn't have a P. And just so we have this warning in advance, like this could have been H, H, or H, H. It does not matter, all right? All that matters is that you have one thing attached to the other thing. All right? For Lewis structures and electron dot structures, the orientation of how things are arranged does not matter. It doesn't matter. Stop thinking you have to be put in a certain place. That is where a lot of people get tripped up. And I just want to set up the next example so it's similar to what we saw for the CH4 and CF4 and things like that. So instead of H2, what if we had F2, diatomic fluorine, which does the same type of thing as diatomic hydrogen? Well, fluorine, as we look at the periodic table, fluorine, group 17, 7 dots, fluorine, 1, 2, 3, 4, 5, 6, 7 dots. I see 1 potential bonding location. That is a high energy species. A potential bonding location means that a bond is going to form there, all right? And it's convenient for that bond to be with another fluorine, right? So I guess that would be an electron dot structure, and that would be your Lewis. And it doesn't matter the orientation in 3D space for those things. So the first compound we're going to look at is our oxygen. And this is where things start to go a little bit sideways for you. When you breathe in, you don't just breathe in O, all right? In addition to the nitrogen, you breathe in oxygen, and it is diatomic, O bonded to O. And the question is why and or how? And we can figure that out by looking at the periodic table, counting, and then pairing up dots, which is exactly what we've been doing. Oxygen, group 16 on the periodic table, has 6 valence electrons, 6 dots. And 1, 2, 3, 4, 5, 6. Doesn't matter where I put them as long as I have 2 pairs and 2 single ones, all right? And I'm just planning ahead because my other oxygen is going to have 2 pairs and 2 single ones. And I want things to match up for us there, all right? So as you look at it, I now have a shared pair. I went from, for instance, for that orange oxygen, 1, 2, 3, 4, 5, 6, to 1, 2, 3, 4, 5, 6, 7, which is closer to 8. Remember, 8 was our goal. Now there's a problem here, which is I had 2 potential bonding locations, but I only had 1 thing to attach. I think you can kind of mentally plan ahead and say 2 bonding locations, 1 thing to attach, I must bond to those 2 things twice. Or sorry, to that 1 thing twice. Once again, 2 potential bonding locations, 1 thing to attach, I'm going to have to bond to that one thing twice to use up both of those locations. And so what I generally show when I'm drawing these out is I will cross out these other electrons, and then I'll just put them in up here as I'm forming that other bond. So, I mean, we can put it here and here or whatever, okay? But what you notice now is that they are sharing 2 electrons each, and we get what is called a double bond. The Lewis structure, again, I'm going to start setting these up more how I do them, which is to skip the electron dot structure, oxygen 1, 2, 3, 4, 5, 6, and oxygen 1, 2, 3, 4, 5, 6. And you'll notice I line up the single dots. That's why I would call an obvious bond. Connect the dot. 2, 4, 6, and 1 is 7. That's not 8. 2, 4, 6, and 1 is 7. That's not 8. But I can bond those, so I'll just put it in there. And we have a double bond. Oxygen needed 2 bonds to something. It is convenient for oxygen to form both of those bonds to another oxygen. And that diatomic oxygen is what you breathe in. All right? Then the other approximately 80% of what you breathe in is nitrogen gas, N2. Okay? And if we need to draw a Lewis structure for that, nitrogen's in group 15, so it's got 5 valence electrons, 5 dots. Nitrogen, 1, 2, 3, 4, 5. When you look at that, 3 potential bonding locations. How many things do we need to attach? 1, another nitrogen. 3 bonding locations, 1 thing to attach. We're going to have 3 bonds to that one thing. So I'm going to put my other nitrogen here, dot, 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 dot. How about, all right? We have a bond, which gives us 1, 2, 3, 4, 5. And that's not 8. So let's draw this and this and say we've got another bond between those 2 things. That's 1, 2, 3, 4, 5, 6, 7, not 8, but closer. 1, 2, 3, 4, 5, 6, 7, not 8, but closer. And so if we take these and put them here, now we have 3 pairs that are shared, and each of them has 1, 2, 3, 4, 5, 6, 7, 8 via a triple bond. Now there's a couple things that went on there that you may not like, one of which is I just moved electrons, right? I did that here too. I just took those electrons and put them in there. Yeah, we can do that. Remember when I said you can put the electrons wherever you need to? Well, now I'm doing it, okay? We needed to pair them up. Boom. Now we got a pair. All that matters is the number of pairs of electrons and the number of things attached. And that's what our Lewis structure is showing us. So when I draw this over here, again, you'll see me kind of do it the way I draw everything. I'd be like, wait, nitrogen, nitrogen, dot, 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 connect the dot, right? And then, okay, not 8. I'll take these guys and make a bond. 2, 4, 6, not 8. I'll take these guys and make a bond. And just so we're clear, these X's aren't actually part of the answer, but I think in your notes or when you're doing them, it's good for you to write them out because it's telling you, hey, something happened here to make these. I took these electrons and put them in there. So this happens to be a triple bond. And I'm going to mention a bit of trivia. It's not really trivia. And then we're going to do one more of these, and I'm going to put the lid on this video. So it is worth noting that in terms of double bonds versus triple bonds versus single bonds, in terms of length, a single bond is stronger than a double bond, or sorry, longer than a double bond is longer than a triple bond. So a triple bond is going to be shortest between 2 elements compared to a single bond. And that kind of makes sense because they're going to pull things together a little better. In terms of strength, the opposite is true. The triple bond is the strongest. Is stronger than double, is stronger than single. And we're comparing between single bonds between, say, the same element. Carbon-carbon single bond versus carbon-carbon double bond versus carbon-carbon triple bond. Okay? We're not comparing different elements like carbon-hydrogen single bond, carbon double bond. No. So this is the general rule for things in terms of strength and length. And I want to do one last example here that is relevant and brings things kind of all the way around for us, and that is carbon dioxide. When you breathe out, you're breathing out about 80% nitrogen. Your body doesn't really do anything with that. And about 15% oxygen and about 5% CO2. And those are rough approximations. It may not be something you know explicitly, but it turns out not all of the oxygen you breathe in is used. In fact, it would be very hard to do so. Only about a quarter of that 20% is turned into CO2. And you kind of know this already because when you're hyperventilating, people say breathe into a bag, right? When you breathe the air in from the bag and then breathe it back out, you're going to breathe it back in again. And if there was no oxygen, it wouldn't do you any good to keep doing that. So what's happening is you're kind of limiting your body. You breathe in 20% the first time, you breathe out 15% oxygen. You breathe in 15% oxygen, maybe you're breathing out like 11% oxygen. So with each breath, you're getting less and less oxygen because it gets harder and harder to remove more and more of that oxygen. I know you don't care, but it's just kind of interesting because I think most people assume that when you breathe in, all the oxygen you breathe in turns into CO2. Not the case, all right? And it gets exceptionally difficult to get all of the oxygen to convert. CO2, I don't know what to do. All right, start by looking at your periodic table. Isn't that a skill? Carbon, group 14, we have 4 dots. Oxygen, group 16, we have 6 dots. I can do that. I'm going to put the carbon in the middle because of something we had mentioned earlier, which is lowest electronegativity goes in the middle. Carbon's at 2.5 versus oxygen's 3.5. Or the thing with the most potential bonding locations goes in the middle. That's another way you can think of that. All right. And then we've got oxygen with 6 dots. And I'm going to try and arrange my dots in a logical way. Okay. I always try and get the single dots facing each other because in a Lewis structure, then I just connect the dots. That makes a lot of sense. Looking right now, that carbon by sharing 1, 2, 3, 4, 5, 6. And as you may recall about the number 6, it's not an 8, and that was our goal. If you look at the oxygen, it has 1, 2, 3, 4, 5, 6, 7, which is better than 6, but still not 8. And this oxygen over here has 1, 2, 3, 4, 5, 6, 7. That pink one's not actually a dot. All right. What can we do then? Well, if we have more potential bonding locations, then we can make more bonds, right? And so it makes sense, and I think a lot of people will see this and say, okay, that's good. How can this electron come down to here? Because that's what I'm going to do. And the answer is very simple. You can put the electrons wherever you need to, all right? The electrons will go wherever they need to. This electron is not actually up there, all right? When we look at things in 3 dimensions, this isn't a place relative to this that is, whatever number of degrees apart. So in these Lewis structures, move the dots wherever you want to make it work. So our actual electron dot structure here would be something like that. Again, I'm not super used to drawing electron dot structures because I tend to skip right to the Lewis structures. So same setup over here when you're drawing a Lewis structure. Carbon, 1, 2, 3, 4. Oxygen, 1, 2, 3, 4, 5, 6. Try and get those single dots to line up. 1, 2, 3, 4, 5, 6. Connect the dots. 2, 4, 6, 7, not enough. 2, 4, 6, 7, not enough. 2, 4, 6, not enough. Gone, gone, make a bond. Gone, gone, make a bond. And you end up with CO2. All right? So we'll take a look at some more complicated things and what we do with ions and what we do when the octet rule breaks and what we do with resonance. But for now, we've got a pretty good handle.